If people could take their seats, we're going to start in just a couple of seconds. Okay, welcome to the first High Energy Astrophysics seminar of the fall semester. We have two speakers today, both from CFA. The first is Bogdan. He got his PhD in 2010 from the Ludwig Maximilian University in Munich. He was then for a short time at the Max Planck Institute, and he's been here at CFA since 2011. His work is focused on how gas and supermassive black holes in galaxies, groups, and clusters. And today he's going to be telling us about the missing baryons using X-ray absorption studies.
Thank you. And we also have to welcome Francesca as one of the organizers of the High Energy Seminar. So she and Lorenzo, if you have any questions and you want to give a talk, you should contact Francesca or Lorenzo. I have to tell this. Okay. Not me, no. Also me, maybe. Okay, so I'm going to tell you about detecting the missing baryons using X-ray absorption studies, which we have been doing with Orsi and Randall and Ralph and Bill in the past over 1 year. So let me just give you some introduction about the missing baryon problem. So the baryon density of the early universe, which here I mean early universe is redshift higher than 2, can be measured using various methods, various independent methods. One of them is the Big Bang nucleosynthesis, and the other is using the cosmic microwave background. And these methods point out that the baryon density of the early universe is roughly 0.045. Okay? So this value refers to the high redshift universe. But when you go to the low redshift universe or lower redshift universe, less than redshift of 2, then what you will find is that a significant fraction of the baryons are missing. So if you do a careful accounting of the baryons, you will find that only a tiny fraction, roughly like 7% of the baryons, are in the form in galaxies. Then there is some in CGM, in clusters in ICM, some of that in the cold gas. But all of these traditional form of the material, all of these traditional appearances of the baryons account only for a tiny, tiny fraction of all the baryons. Then you can look at other parts of the universe, namely the warm-hot intergalactic medium, and then you will find that this so-called warm-hot intergalactic medium contains a significant fraction of the baryons, roughly this much. So this is galaxies, CGM, ICM. This is in the warm phases of the warm-hot intergalactic medium. But even if you co-add all this, you will find that roughly 1/3 of the baryons are still missing. And the suspicion is that a significant fraction of the missing baryons is in the form of the hot phases of the warm-hot intergalactic medium. Now I'm mentioning this warm-hot intergalactic medium, but what is this? So this is the low-density filamentary structure of the universe, which follows the distribution of the dark matter. So this image is from a simulation from Illustrious collaboration, and you see all these. So this shows the dark matter density, and you see all this dark matter structure, and this warm-hot intergalactic medium is the gas which is sitting in these structures, in this filamentary structure of the universe that connects galaxies, galaxy groups, and galaxy clusters. Now the temperatures, as the name suggests, this is warm-hot, so it has a very wide range of temperatures. It has 10 to the 5, 10 to the 7 Kelvin. As such, it's observable using UV and X-ray wavelengths. Given that everybody is interested where the baryons are, there have been a number of studies to search for the missing baryons. Okay? And it's a very popular topic to search, to identify where the missing baryons are. Now you want to search both in the UV and in the X-ray to detect both the warm and the hot parts of this WIM, or the warm-hot intergalactic medium. So the warm phase of the missing baryons is now routinely detected and routinely observed using HST, for example. Okay? But there are difficulties with observing the hot phases, so the X-ray part, using Chandra or XMM Newton. Why is that? If you look at these images and the numbers below these images, you will immediately find out. The issue with the big difference between UV and X-ray spectrographs is the effective area and the resolution of those instruments. So whereas the Hubble COS, or the cosmic origin spectrograph, has an effective area of roughly 2,000 square centimeters, the Chandra LETG, so the low energy transmission grating, which you would use to apply absorption studies, has an effective area of roughly 14 square centimeters at the wavelength of oxygen 7, which is the most significant or the most abundant and strongest transition expected from X-ray absorption lines. So this is like 2 orders of magnitude difference. And even though we expect higher column densities in the X-rays, it is extremely, extremely difficult to detect X-ray absorption lines using Chandra or XM Newton because of this difference in effective area. And also the resolution, if you look at the resolution of HST course, is roughly 20,000, and you can compare that with the Chandra LETG, which is, again, only around 500. So this is the reason why the low density, so what I mean is low density, is really the low density hot phases of the OVII remain undetected. So there are claims which suggest that the densest part of the OVII have been detected both in emission and in absorption, or even outer halos of galaxies, but the really low density part, as I will show you, remained undetected until a very recent study. So how are these absorption studies working? So you can imagine that you have a bright AGN here, and you have Chandra here on the other side. In between, there are all these filaments which are filled with hot gas. Now the photons from this bright AGN are passing through these filaments, and then there are metals in the hot gas, and then while it's passing through these filaments, absorption lines from this gas are imprinted in the spectrum of the AGN. Okay? So what you have essentially, if you look at the X-ray spectrum of the AGN, what you will see is little dips, little absorption lines in the spectrum of the AGN. This is all nice, and this works nice in the UV. In X-rays, we have difficulties, of course, and one of the difficulties is that this method, by definition, is a so-called blind search. So what does a blind search mean? Blind search means that you just look at the X-ray spectrum, and when you look at the X-ray spectrum, you search for little dips. You don't know, and you don't know the redshift of that. You don't know where that is coming from. You don't know essentially the redshift of the filament. You just assume something. What do you assume? You assume that it's coming from oxygen 7, which is again the most abundant line and the strongest transition. So oxygen is the most abundant, and oxygen 7 is the strongest transition expected in X-rays. So you assume that it's coming from oxygen 7. And then you infer from the redshift of the observed dip, or from the wavelength of the observed dip, you infer the redshift of the filament. So by definition, this is a blind search, and this will result in a tentative detection. You cannot be sure that it's actually oxygen 7, and you cannot be sure that it's a real signal or some instrumental noise. Okay? And this makes it extremely difficult to actually detect anything, especially given the low effective area and the noisy spectra. Okay, so I say again, so no detection using individual sightlines of the low density and hot phases of the OVII have been made so far. So we wanted to improve on that. And when you want to improve on a field which is suffering by the low number of counts, then what you do is you stack, right? That's the trend. So, and what I'm going to show you here is I'm going to introduce a new method using this quasar H1821 plus 643, which is an extremely bright quasar. It has a flux of almost 10 to minus 11 and a redshift of 0.3. So this is a very popular quasar because it's not too nearby, not too far. So we expect many filaments between us and the redshift of this quasar, but it's still not too far. So we get a sufficiently large number of counts, so it can be observed with Chandra LETG, and we get a huge number of photons. As such, it is an excellent target for both UV and X-ray absorption studies, and has been widely observed with HST and Chandra as well. So I told you the keyword is stacking. So we want to do it in a smart way. You want to stack. So what we want to do is we want to stack the absorption lines. We want to stack the spectrum of the AGN many, many times, and we want to stack according to the redshift of the filaments. But how do we find out the redshift of the filaments? In order to do this, we need previous detection of UV absorbers. Okay? And then we assume that, okay, if it has warm gas, then it will have hot gas as well. Okay? So that's why we need UV absorbers. So we need HST studies. Then we also need a previous study of the quasar field to search for galaxy redshifts. Then what we can do, we can cross-correlate the redshift of the absorbers, so of essentially the galaxies in the filaments, and the redshift of the galaxies. So we will know which galaxy sits in which filament. Then we can cross-correlate these two, and we can also add the fact that we know the galaxy properties from follow-up SDSS observations, for example. And if we know all this, then we can stack the individual absorption lines, which will result in a direct non-tentative detection. Why is that? Because we know the redshift of all absorption lines, okay, from the UV studies. And because we stack many systems, we will have much, much larger signal-to-noise ratios than before. And as such, we can detect very narrow lines, which would be impossible to detect using a single channel observation. So let me just go through these couple of steps one by one, because that's the key part of this whole project. So we want to stack the X-ray line forest. In order to do that, as I mentioned, we need previous detection of absorbers. So in the case of H1821, there has been HST observations of UV Lyman alpha absorbers by HST. And again, these provide the accurate redshift of the absorbers. So now what we know from these HST measurements is the redshift of the filaments. Okay. And here I show a Chandra spectrum. So this is a Chandra LETG spectrum. And we show all these vertical lines show the expected position of the oxygen 7 line at the wavelength of the absorber. So the wavelength of the oxygen 7 line is 21.6, and if you redshift this, you see that you can find out that the redshift of the absorbers go from 0.06 to 0.27. Okay? And here I show the 17 absorption lines which we use to stack at the end. Then we also have an optical survey of the galaxies in the quasar field. So there has been a spectroscopic redshift survey of 154 galaxies in the 1 square degree area of this quasar. So the quasar is here, and the yellow little symbols show all the galaxies which belong to an absorption, which belong to a filament. Okay? So these galaxies are sitting in filaments. Then we also use follow-up SDSS imaging to find out everything about the galaxies, the mass. We use the stellar mass to halo mass relation to find out the halo mass, and we basically know everything about the galaxies. Then we cross-correlate the Lyman alpha redshifts, so the redshift of the filaments, with the galaxy redshift. Okay? So altogether, we found 24 Lyman alpha absorption lines and galaxy redshifts that are matching, which are sufficiently close to each other. Then we measure the galaxy properties using SCD fitting, the stellar mass and the halo mass from the halo mass, stellar mass halo mass relation, and as I mentioned. And then we do one more step, which is filtering the galaxies by mass. We need to filter the galaxies by mass. Why is that? Because more massive galaxies tend to live in bigger filaments, in denser filaments. Okay? You see here this simulation image, and here is a dense filament, and here is a low density wall. The size of these circles or points are proportional with the mass of a galaxy. And what you can see here that in denser filaments you have bigger galaxies, more massive galaxies, and in low density regions you have low mass galaxies. Okay. So at the end, we are left with 17 Lyman alpha systems that belong to massive galaxies. Now let me just go to the Chandra data. So the Chandra data, as I mentioned, it's LETG ACES data of H1821. The exposure time is 470 kiloseconds. We have 17 redshifted absorption lines, which we are going to stack. And if you multiply this number, 470 kiloseconds times 17 absorption lines, you will find out that we have 8 megaseconds of exposure altogether. So if we co-add everything, if we shift the spectrum 17 times, then what we are going to have is an equivalent of an 8 megasecond deep Chandra exposure. So again, the idea is that we have a weak or a non-detected or something at the redshift of the absorption lines. So here, for example, this is at 26 angstroms. So this is just an illustration, right? This is 26 angstroms, and redshift corresponds to a redshift of 0.2. Assuming that it's an oxygen 7 line, this is at 24 angstroms, redshift of 0.1, 0.06 redshift, and 23 angstroms. The idea is that in the individual spectra, you see nothing, or just little noise, or a very weak signal. But if you shift everything back to the rest frame wavelength, so 21.6 angstroms, and then you co-add all this, then what you might get is a statistically significant detection of an oxygen 7 absorption line at 21.6 angstroms. So this is the theory, and we also had to do that. So Orsi was doing all this work. She spent roughly a year doing all these steps, which I summarize in like 10 seconds now. So she was eliminating the overlapping redshifts to make sure that we are not co-adding the same part of the spectrum twice. She was blue shifting the spectra toward the rest frame wavelength. Point number 3 is blue shifting the response and the R files. Then we were rebinning the spectra and response files on the same wavelength grid, cropping the spectra and the response files, and then finally stacking the spectra. So this all sounds easy, but in fact it's not easy. But we have done it. And at the end, as I mentioned, we get a single spectrum shifted to the rest frame wavelength, which has an 8 megasecond total exposure time. So the next slide is the result. So let's see if we stack 17 times the spectrum of age 1821, then what do we get? So here it is. So this just counts, and this is the wavelength, and the yellow line shows the expected position of the oxygen 7 line. So what you see here, and then the blue line is the fit. So what you see here is that the deepest point here, well, first of all, you see something which looks like an absorption line, right? Kinda? Okay, I see people measuring, looking at you, Esther, yeah. So the deepest point is at 21.6 angstroms, and then you have another 4 or 5 points around 21.6 angstroms, and this whole thing shows a Gaussian line profile. When you fit it with a Gaussian line model, and then this is a power law fit, then what you find out is that you have a detection significance, so this is from XPEC fitting, a detection significance of 3.3 sigma. The equivalent width of this line is 4.1 milliangstroms, and the corresponding column density is roughly 10 to the 15. Now, it's very important to mention at this point that this 4 milliangstrom refers to the sum. Okay, so this is not an individual absorption. This is not an individual absorption line, but this is a sum of 17 with some unknown distributions. So some of them might contribute more, some of them might contribute nothing whatsoever. But given that we knew all the redshift that we stacked, I can say that this is the first statistically significant non-tentative detection of an X-ray absorption line of the WIM, the hot phases of the WIM. So I told you that that 3.3 sigma statistical significance comes from XPEC fitting. But we have done also Monte Carlo simulations to find out what is the chance coincidence that we just picked we got 17 random redshifts, which we think is we selected them in a smart way. But what is the likelihood that this is just due to chance coincidence, that we are unlucky and we just picked the 17 wrong redshifts, which ended up in this signal? So in order to find this out, we picked 17 random redshifts in the redshift range between 0 and the redshift of the AGN. And so we picked 17 redshifts, and then we repeated the whole procedure. So we stacked the 17 redshifts, just like we did with our real data. And then we did this whole procedure 10,000 times. Then we fit each line, or this part of the spectrum, in the same way as we did with this one, and then try to find out what is the detection significance. And this plot shows the detection significance on the x-axis and the frequency on the y-axis, the normalized frequency on the y-axis. As you can see, and this is just a simple Gaussian. Okay, so this is not a fit. It's just a standard normal distribution here. So the peak is around 0, and this is an absorption. This would be an absorption line because -3, and this would be an emission line because it's +3. So altogether, we have 3 spectra which show a 3.3 sigma or greater than 3.3 sigma detection out of 10,000 trials. So the chance coincidence that we got this spectrum just by chance, randomly, is 3 times 10 to minus 4. However, one caveat is that the actual randomly stacked spectra, which have more than 3 sigma detections, don't look like our profile. Okay, they look ugly. If I was showing you one of these random 3 sigma detections, you would laugh and you wouldn't believe me. Okay. So the real chance coincidence is actually lower than this. Now we were also verifying our stacking method, whether it's sufficiently accurate or whether it works. And in order to do this, we asked the question whether can many small significant sigma result in a statistically significant detection. So in order to do this, we use the fake it with XPEC. So we modeled 17-week absorption lines, and then we co-added these. Okay? And all these weak absorption lines had, you wouldn't see anything in the spectra, so they were essentially noise. We repeated this for 10,000 sets, and then what we found is that we get a statistically significant detection in the stacks. So the mean detection of these 10,000 fits is around 2.8 sigma. I also show you the other wavelengths. So I showed you an oxygen 7 detection. We also looked at other lines. So this is oxygen 7, or the wavelength of other lines. You see nothing. You can put an upper limit. Nitrogen 5, nitrogen 6, neon 9, neon 10. You don't see anything in any of these. Now you can also make various calculations about the missing baryons. So you can assume a typical metallicity from simulations. So the typical metallicity of filaments is roughly 0.07, an ionization fraction of 0.75, and you can compute based on this, you can compute the cosmological mass density of oxygen 7 absorbers, which is roughly 0.039. If you remember the number on the very first slide, that was 0.045, so which suggests that roughly 10% of the baryons are in the hot phases of the OVII, which are detected through oxygen 7. And this is actually comparable with simulations which predict 15%. Okay? So according to these simulations, we don't expect that all the 1/3 of the missing baryons should be in the hot phases of the OVII. There are still some low density part of the warm phases of the OVII which haven't been accounted for. If you look at the number of so this you can also compare the number of absorption lines per unit redshift with simulations. Here we assume that every absorber contributes equally, which is not necessarily true. But you see here the column density and this number of absorption lines per unit redshift, and this dotted line shows a simulation. And you see that the fraction of missing baryons are actually in the OVII, which is coincident with the simulations. Now this gets better, because you can also bin the absorber. So you might remember that we had 17 absorbers, and we can divide them into 2 bins as a function of their impact parameter. So impact parameter means that what is the projected distance between the AGN and the filament. And I should note that all of these galaxies are actually have an impact parameter which exceeds the Virial radius. Okay, so we are not tracing all but one. So we are not tracing here the galaxy halos, but what we are tracing here is really the VIM. So we divide the absorbers into 2 bins, just for example like this. Here is the AGN. This inner circle could show these galaxies here, galaxies and absorbers here, and systems in the outer circle could be here. Okay, so this is megaparsec. So this is 1 megaparsec, and this is roughly 4 megaparsecs. And this shows the column densities in the 2 bins. And what you can do is you can assume a typical path length for the VIM filaments. If you assume a path length of 5 megaparsecs, then you can, from the column densities, you can immediately compute a density, or hydrogen density actually. You compute a hydrogen density, and you get hydrogen densities of 10 to minus 7 in the VIM filaments. Okay? And just as a comparison, I show you the density profile of a massive spiral galaxy. This is from my own work from a couple of years ago. And you see that the typical gas density in the halo of a massive spiral galaxy is roughly few times 10 to minus 4. If you fit this profile, You extrapolate, you go out to the via radius, which is roughly here at 400 kiloparsecs, then it's still 10 to minus 4. And here we are roughly 2.5, 3 orders of magnitude below. So we are probing gas which is 2.5, 3 orders of magnitude less dense than the halos of galaxies. Okay? And
what's the over density?
Look at the next slide. Here. So the typical overdensity of this gas is actually around 1, which is typically expected for in WIM filaments.
I thought it was tens, ones.
In WIM, it's around the ones. You can look at that. Okay. So what we are doing here is we are trying the lowest density part of the WIM. And I think my time is up, and that's it. Thank you.
It's a lovely result. Oh gosh. The stacking must introduce some artificial line broadening to the equivalent width and the line width, just because you're regridding and blue shifting. But is that a super small broadening, or is it large compared to the measured line width?
It's small. Yes, it's small. It's one. Yeah, it's small.
Nice result. So I remember reading a newspaper a month ago by the et al. So how does your real compare to
So their density. So his density is like. I asked him. His density is like 3 to 5 times 10 to minus 5. Okay, so what he's probing is really the outer halos of the galaxy. Okay, because his impact parameter, well, he's again, that's a blind study, but so what he's claiming in his paper is that the impact parameter is fairly small. Okay, so that the absorbers could be, so you could see actually the outer halo of a galaxy. So by no means is he probing this part, the WIM, but he's more likely probing maybe within the via radius of the galaxy or just beyond the via radius of the galaxy, but his densities are 2 orders of magnitude higher than ours.
This is a really nice result, but how are you accounting for the fact you've got 17 different filaments, all at different impact parameters that you're putting up here? But how do you normalize in any way for what the UV is telling you the density of each filament is?
Well, we don't.
But
We just stack everything.
Okay. But the fact that you're stacking over a whole range must introduce.
Yeah, so some of them, yes, so that's admittedly an issue, but that's the nature of stacking, with which you cannot do anything. So some of them will contribute more, some of them will sit in a denser filament, some of them will sit in a weaker filaments. If you do stacking, I guess that's the best you can do. If you it's by any other means you wouldn't be able to achieve this kind of low densities.
Must introduce some, let's call it systematic error in what the overdensity could be.
Yes, so yeah, these values are again some average values, yes. So everything is an average here.
So I understand how 17 low significance absorption lines would add up to give a higher significance, but isn't it also possible that if you just had, if you're selecting a bunch of random downward fluctuations in the spectrum and you add them up, you would also just get
Yes.
an artificially high significance, right? And so to make sure that the 17 things that you added up are not just random fluctuations, wouldn't the test be that you also end up finding other absorption lines once you've shifted them all into the rest frame?
I'm not sure if I understand the question, but so in order to make sure that we are not, that it's not random chance, I mean, we did these Monte Carlo simulations, right? We did these Monte Carlo simulations where we just picked random parts of this, well, we randomly shifted this spectra 17 times, and then we repeated it over and over again, and just checked whether our stack, or how likely it is that our stack is a result of a random chance.
Sure, but
And-
it was random shifting, but it wasn't randomly shifted so that every shift ended up in adding a dip.
Yes.
you
So
know?
what we have, I'm still not sure, but what we have been, so we also checked the individual wavelength, individual redshifts, but there is not. So there is nothing systematic there. Okay? So basically, what we are doing, we are collecting a lot of noise, and at the end, we get something nice.
But you're not just picking dips, right? You're picking redshifts that
We are picking.
come from independent.
Yes. We are not. No, we are not. Yeah, yes, exactly. So we are not picking dips. We are not doing a blind study. We have a set of redshifts which are coming from UV measurements. We don't define those redshifts. They are coming not from us. Okay.
Last question.
So is the line width you're getting, is that thermal or is that a lot wider than
I think it's thermal. Yeah.
Okay,
Yeah.
let's thank Akush again.
Thank you.
If you have more questions, he's conveniently here, so you can ask him anytime. Our next speaker is Gabriella Alvarez. She is a grad student coming from Vanderbilt University, and she's doing a pre-doc here. She'll be talking to us about the work that she's doing, also looking at the intersection between cluster environments and intercluster filaments.
Can you hear me? Yeah. Cool. All right. Hi. So first, thank you, Francesca, and I'd like to just thank my collaborators. This work would have been impossible, or it would have at least taken much longer without their help and input. So first, a quick outline. I'll briefly go into some background into galaxy clusters, and more specifically their outskirts and large-scale intercluster filaments. Then I'll motivate the topic. And then I will talk about observational intercluster filament studies, as they are few and far between. And then finally, I'll conclude. Okay, so galaxy clusters, what are they? They're the largest known gravitationally bound structures in the universe. So here on your right, I'm showing max J0717.5 plus numbers. And so we have the optical image over here, and you can see a crowded field of galaxies. And the pink is tracing dark matter from weak lensing studies. And the blue is tracing the hot ICM emission that permeates the galaxy clusters. And so we're going to be focusing today on this hot X-ray gas. And so here's a simulation of a galaxy cluster. On your left is surface brightness, and on your right is temperature. And in this circle right here is R500, and that's usually where cosmology studies are done, because that's the most virialized part of the galaxy cluster. And as you can see, as you move out in radius towards R200, and 4/3 R200, even out to 4 R200, the galaxy cluster becomes less and less homogeneous as you look azimuthally, less relaxed. You have galaxies and groups falling in through these long filaments, and everything just starts to get a little more messy, and the thermodynamic state is not in equilibrium. And you can also see that in temperature as well as you move out to larger radii. Okay, so now let's talk about intercluster filaments. First, I would like to point out this is from the most recent suite of simulations from the Illustrious team, the next generation. And this is a 100 megaparsec box, so 100 megaparsecs along here, 100 megaparsecs here. And this slice is showing you surface brightness, and you can sort of see shocks from gas accreting onto these galaxy clusters. So here would be a cosmic filament, another cosmic filament, and these are galaxy clusters which form inside and at the nodes of these large-scale cosmic filaments. So today we're going to be talking about intercluster filaments. So these little small regions in between clusters before they eventually probably merge and become a larger galaxy cluster. Okay, so here's a slightly older pie chart of the baryons that we think are missing. Again, there's a small percentage that we see in galaxies in the intracluster medium gas and cold gas. And you have some baryons that we've counted up from the Lyman alpha forest, and some tentative wind detections have been sliced out over here, and we think the WIM should really be taking up more of this missing baryons portion that we just haven't seen due to the low surface brightness nature of the WIM gas. And so what we expect from the WIM, I'm showing here temperature in Kelvin. We would expect it to be around 10 to the 5 to 10 to the 7 Kelvin, or 0.01 to 1 keV. And we would expect the density to be around a few times 10 to the minus 7 to a few times 10 to the minus 5 per centimeter cube. And that's the electron density. So another reason to study intercluster filaments is if you have an intercluster filament orientation close to the line of sight, the projected surface brightness of the gas is much higher than, say, a filament orientation in the plane of the sky. And so if we have higher surface brightness gas in projection, then it would be a little bit easier for us to get a direct detection of the WIM. Okay, so now let's talk about thermodynamic state for a little bit in galaxy cluster outskirts. These plots are a little busy, so I'll take some time to go through them. This plot on the left is for SZ detected clusters. And on the y-axis, we have entropy normalized to entropy at R500. And on the x-axis, we have radius normalized to the radius at R500. And entropy defined here is specific entropy, which is the temperature times the electron density to the minus 2/3. And so these dashed lines are showing what we would expect the entropy profile to look like for these galaxy clusters if they have formed from pure gravitational collapse, like we want for our cosmological measurements. What we see in reality is a little bit different. So these left two panels are for cool core clusters. These right two panels are non-cool core, and the middle two panels are non-cool core, and the farthest right are just all these clusters combined. On the bottom, we have higher redshift clusters, and on the top, we have lower redshift clusters. So if these clusters have formed from pure gravitational collapse, we would expect that these measurements would lie along the self-similar line. Clearly, we don't see that. In the center, which I'm not going to focus on too much, we have other thermodynamic processes happening, such as AGN outflows and from the brightest cluster galaxies. So usually these regions are excised for cosmological studies, and we're really looking at from here up until R500 for cosmology. And so, and that's worked out really well for the last couple decades. But now, as we're able to start looking past R500, we're starting to see that the entropy profiles actually are starting to flatten at large radii, which you would kind of expect if you recall the images of the galaxy clusters at large radii. You saw that there are filaments and things falling in, and it's messy, and there are other thermodynamic processes happening. And so you see entropy flattening again for these low redshift non-cool core clusters at low redshifts, and entropy flattening even for the whole sample at high redshift again. And so now here, this plot on the right is, again, entropy normalized to entropy at R500 and radius normalized to the radius at R200. And this is the work done by Stephen Walker in 2013 with Suzaku clusters. So now we're looking at clusters in X-ray via Bremsstrahlung radiation. And so again, here's the self-similar prediction from simulations. And we see, again, a departure from that at low cluster radii, which we expected. And then now we can see out to R200 with this study. And you can again see entropy flattening at large radii, again hinting that the thermodynamic state is not in equilibrium. And there are other processes going on. So the leading theory for this entropy flattening phenomenon is that there are unresolved cool clumps at large cluster radii, which you sort of saw in the surface brightness images I showed you a couple of slides back. There could also be many other processes at play, such as electron-ion non-equilibrium, turbulence, weakening accretion shocks. More recently, the XCOP collaboration, and more specifically Vittorio Giardini, tried to remove cool clumps at large cluster radii from their analysis, and they found that most of their clusters actually didn't flatten at large radii, and were closer to the self-similar line. But again, in their study, they still had a couple of clusters that were flattening at large cluster radii, again hinting at other thermodynamic processes at play. Okay, so now I'm going to start talking about intercluster filament studies that have been done in the X-ray. So here is a study done by Werner et al. In 2013 of a Bell 223 up top this double peak cluster, and a Bell 222 in the south. And this is a wavelet decomposed image, and they use these yellow circles for background and this red circle to fit the filament properties, the intercluster filament properties. And they actually detected a temperature of 0.9 to 1 keV, depending on how you want to fix your metallicity. Akos just showed us that he was able to constrain the metallicity for these filaments a little bit better, but they're still really unknown. So you can vary anywhere from 0.1 solar to 0.3 solar. And so this was the first direct detection of this densest part of the WIM. And more recently, Ezra and friends did a study of a Bell 1750. Here on the left is Suzaku observation, 1750 north, center, and south, very faint at the bottom. And here is the corresponding Chandra observation on the right, used to mitigate point sources, because Suzaku has a very large PSF. And so, first of all, Ezra found that looking somewhat azimuthally at the entropy profiles for these clusters, that they actually did fall on self-similar at large cluster radii, which is curious because, as I showed you a couple of slides back, many massive clusters seem to flatten. Their entropy profiles seem to flatten at large cluster radii. So this may hint at a mass dependence, but this field is quite young, so there's a lot more work to be done for that. And second of all, Ezra found in these two northern regions along the putative interfilament axis with her two temperature fits that first of all, the two temperature fits were better than the one temperature fits. And second of all, she found cool gas ranging from around 0.8 keV to 1 keV, depending on how you want to fix your metallicity. And so another detection of the dense end of the WIM, which is pretty cool. And now we'll look at a Bell 98. On the left is a Suzaku image that I made, a Bell 98 North, a Bell 98 South, and a Bell 98 South-South. Here's a Chandra image made by Rachel Paterno-Maller et al. Done here again. And so she didn't find any hints really of the WIM. There is a hint of this bridge of emission. The Chandra observations were quite shallow, and Scott recently got more time to look at this region, so it'll be more telling whether there's a bridge or not. And they saw hints of a merger shock actually in between these two clusters. And now with the Suzaku observations, we'll be able to do a similar analysis as Ezra and look somewhat azimuthally, first along the putative filament axis and then off axis, again to investigate entropy at large cluster radii and to look for the WIM. And there seems to be a bridge of emission in this image, but again, the PSF for Suzaku is quite large, so it requires some more investigations. So keep your eye out for that work coming soon. And now I'm going to talk more in depth about a Bell 3391 and a Bell 3395 and the intercluster filament in between them, because that was the most recent work published in March. And so here's a ROSAT image from Titley and Henriksen from 2001, a Bell 3391 in the north, 3395 in the south, and this is actually a double-peaked cluster. You'll see better images of that in a second. And sitting in the middle is this galaxy group ESO 161. So what they found from this study, after performing a dynamical analysis of the system, is that they thought the filament orientation was close to the line of sight. And again, that means that the projected surface brightness would be much higher for a filament orientation along the line of sight versus in the plane of the sky, which again makes this system ideal to study and look for the WIM. And they found also excess emission in this filamentary region after making beta models for these two clusters and subtracting them, so hinting that there's actually a filament there and it's not just two overlapping halos. Okay, I'd be remiss if I didn't mention Planck and SZ. So again, here's A3391, A3395 system, and they've rotated it to match, to be able to match up other systems that they were looking at. And so here on the top, the axes are just in arc minutes, and this color bar is for the Compton Y parameter. And so here's the actual observation. This middle panel is the beta model that they performed for each cluster. And down here is the residual. So as you can see, sort of, there's excess emission in this filamentary region, again hinting that there is an intercluster filament there and not just two overlapping halos. Okay, and here's a Suzaku observation. Here's the double-peaked A3395 up into the filamentary region. And so in this analysis, Sugawara et al. Found a flat temperature profile up into this filamentary region that is above what one would expect based on the universal temperature profile for A3395 and the universal temperature profile for A3391. And ESO 161 is sitting somewhere over here. And so they attributed this flat temperature profile to a merger shock. And so we'll get back to that. Okay, so finally here's our data here's Chandra on the left. Here are the regions that we use for the filament profile. Here's ESO 161 sitting in the middle, A3391 in the north, and A3395 in the south. And again, you see that double peak. And this cyan circle is the field of view for XMM Newton, shown here. ESO 161, the bottom of A3391, and the top of A3395, and this tentative bridge of emission over here. And so now let's look at our temperature profile. The green triangles are the XMM Newton measurements. The blue dots are the Chandra measurements. Again, we're looking north to south, and here's temperature in keV on the y-axis. And these black stars are for the same regions, but including the group emission. And so our temperature profile very well agrees with what was found with the Suzaku data, in that it is flat, and the temperatures are decently high. As I said earlier on in the talk, for the WIM, we would expect a temperature of around, for the dense end of the WIM, we would expect a temperature of around 1 keV. And so we did perform 2 temperature fits for all of these regions. I'll show you them again, north to south. We find in region 2 and 3 low temperature gas. In region 3, for our 2 temperature fit, we found a second temperature around 1 keV. In region 2, we found a second temperature of around 0.3 keV, which sounds very promising for the WIM. But if you compare the temperature profile for ESO 161 to these regions, they match up pretty nicely. So we're more inclined to think that maybe we missed some emission in the north, which I will further motivate in a couple of slides, and that those low temperatures are attributed to the outskirts of the galaxy group. And so here now I'm showing a very busy plot. Take it with a grain of salt. Again, of entropy on the y-axis and radius as compared to normalized to R200 on the x-axis. And this is the self-similar line for A3391. The green is a self-similar line for A3395. And these top 2 panels are the entropy profiles for the filament if its orientation is in the plane of the sky. And even for that orientation, we find that the entropy is just much too high to be associated with the WIM gas, which further leads us to believe that these clusters are undergoing an early stage merger, and their ICM gas is being pulled into this intercluster filamentary region. Okay, so I want to take a second to talk about ESO 161 because it's pretty cool. Here's a close-up of this galaxy group in Chandra, and here is a photon image from XMM Newton and a curvelet decomposed image that Bogdan performed for the galaxy group. And we actually find in our surface brightness profile that there is an edge in this leading part. And we find tentative evidence that there are 2 ram pressure strip tails. So we think that this galaxy group ESO 161 has sort of come in from the northwest, and it's being ram pressure stripped in the outskirts of A3391, which actually suggests an in situ enrichment scenario, which is pretty cool. Okay, so the study of galaxy cluster outskirts and large-scale intercluster filaments is a relatively new field just because of their low surface brightness nature. But with their really exciting missions that are coming up, such as Eurozeta, Athena, Charm, Axis, and Lynx, that will be able to start to really probe these low surface brightness regions. So it's going to be exciting. Thank you.
Questions for Gabriella? Okay. Well, she is here as well. And so please feel free to approach both of the speakers later on. And let's thank both of them again.
Not too bad. I didn't get any questions.
It's just because you're such a badass. It's irrefutable.
Yeah, thanks.
Yeah. Nobody questions.
You're organizing the conference.
I'm helping to
Talk.
organize, yes.
Okay.
Yes.
Ben Oppenheimer's going to be here. I don't know if you know Ben from Colorado.
I am familiar with him.
Okay.
I haven't met him. But
Okay.
yes.
He'll be here off and on over the next year. So I was talking to him yesterday over Skype. You know, he's interested, and it would be good, very good to have him give a talk at some point. I'm going to send you an email, and I'll CC him. You don't need me to be in the middle of it, okay?
Perfect. Yeah,
But you know, I'm sure he has enough stuff that if you're looking for somebody to talk for the whole hour too,
Yeah.
that he would be fine. But even as a half hour, either way. But I'll let you and him take care of that, okay?
Sounds great.
Okay,
Yeah,
great. Thank you.
That's my life now. I've become a deep sky optical astronomer the way I imagined that might be when I was 12 years old.
It should be roughly.
Yeah, well, this April 33, we must have done a much better job with SPT because it's in our field. And we are 30 times deeper than Planck and 3 times higher resolution. So